In this video, we look at section 3.4 and some of the preliminary ideas around complex numbers. Complex numbers are going to show up quite a bit in this section. Okay. Basically, the idea that there's a number I, and the number I is defined by when you square it, you get -1. Okay, so this is the definition of the complex number I. Okay, an alternate definition is that I is the square root of -1. Okay, so in this section, we're going to see complex numbers quite a bit, so just some preliminary ideas. So for example, if you have the number 1 plus I, and then you multiply that by the number 1 minus I, right? You can distribute this just like you would. 1 times 1 is 1. 1 times negative I is negative I. 1 times I is positive I. I times I is I squared, and then there was a minus there. So notice in this case that you can do complex arithmetic. The number I minus I is going to be 0. I squared is -1. -1 is 2. Okay, so you can do arithmetic with I. So if you also want to say something like, what is 2 plus I plus 4 minus 2I? All right, notice that this is a general complex number. Right? Complex numbers are of the form A plus I times B, okay, where A and B are real numbers. Okay, so if you're going to do adding of two complex numbers, the result needs to be another complex number, something times I, and you basically just add the real parts and add the complex parts. So, for example, with this number 2 plus I, typically it's called Z. We'll call it Z1, the first complex number, right? The number 2 is denoted as the real part of the complex number Z1, or the real part of the complex number Z1. So notice when you're talking about the real part of a complex number, the answer is a real number. Okay. There's also a complex part, or imaginary part of a complex number Z1. This is the imaginary part of the complex number Z1. The imaginary part is 1. It's the number in front of the I. Notice that the imaginary part of a complex number, even though it says imaginary part, it's still a real number. Okay, so a follow-up to that, you have another complex number, Z2, is 4 minus 2I. The real part of this number is 4, and the imaginary part of this complex number is -2. Both of the numbers 4 and 2 are real numbers. Okay, so there's how you would do some arithmetic with complex numbers. So 2 plus I plus 4 minus 2I, you just do component-wise 6 minus I. Okay, which is a new number Z3. Okay, so if you take the complex number Z1 plus a complex number Z2, you get a new complex number Z3. Okay, so there's some complex arithmetic and the idea of the real and the imaginary parts. There's going to be a key formula. Okay, so let's extend this idea. Extend to vectors. What about this if I take the complex number I times the vector 1, 2? Okay. It would stand to reason that this would be 1 times I, 2 times I, right? Otherwise known as I, 2I. right? So you can treat the complex numbers as just complex constants k1. So this would be constant k1 times v. All right. You can do complex arithmetic. Let's say you do 2I times the number vector 1, 2. Okay, minus I times the vector I, 3. Okay. So notice that this vector has the complex number I in it, and the constants k2 is a complex number. So you could do the arithmetic here. Be 2I, 4I. So now you have a vector with complex number entries. Okay. You have a constant here. You can multiply it through, so it would be plus. You get negative I squared, and then you get minus 3I. I squared was negative 1. Negative 1 is positive 1. Okay. So you could complete the addition here, or complete this complex linear combination. To get the answer 2I plus 1. 4I minus 3I is I. So what we're setting ourselves up here is the idea that we're going to do, we're setting up the idea that we're going to do a constant k times y1 plus a constant k y2. We're setting up for the linearity principle. With the possibility that k1 and k2 could be complex numbers. And we're also setting up that y1 and y2 can be complex vectors. Okay, so the same processes happen. You just have to be able to deal with the key idea that I squared is the number -1. Okay, so that's some of the first complex arithmetic we would need to remember. The next idea, the absolutely key formula for anything with complex values in it in this section is what's called Euler's formula. Euler's formula is e to the I, typically written as e to the I theta, is cosine of theta plus I sine of theta. Okay, so what we mean by using this formula, for example, is that if you have something like e to the 2I, okay, theta in this example is 2. The answer to that would be the cosine of 2 plus I times the sine of 2. Okay. Or if you have another example, e to the minus I theta, right? What we're seeing here is theta is actually negative theta. So you would get cosine of negative theta plus I times the sine of negative theta. And then use the fact that cosine is an even function and sine is an odd function. So e to the minus I theta is cosine of theta minus I sine of theta. Okay. You can then ask the question, what's e to the I theta plus e to the negative I theta then? Okay, e to the I theta is some complex number z1. E to the minus I theta is some number z2. What is the new answer as a complex number? Well, e to the I theta was cosine of theta plus I sine of theta. E to the minus I theta is cosine of theta minus I sine of theta. Okay. And you collect, we're adding these together by adding the real parts, so you'll get cosine of theta plus cosine of theta, and then factoring out the imaginary number, right, you would get sine of theta minus sine of theta. Okay. So doing these two complex numbers, you get 2 cosine of theta plus 0 times I. Okay. So what you could say here is that the real part of e to the I theta plus e to the negative I theta, the real part is 2 cosine of theta, and the imaginary part of this complex number happens to be 0. Okay? It's still a complex number. It's of the form something plus I times some other number. It just so happens that the imaginary part of the number is 0. Okay? So this is an absolutely key formula, Euler's formula, that we're going to need in this section. Okay? The way it's typically going to appear is as follows. For example, you will have, let's say you have a vector y1. Okay. And let's just say we're not sure where it comes from, but let's say it comes out to be I times e to the I theta. E to the IT, sorry. And then we'll say it comes out to be I. Okay, so remember we've got a vector of complex numbers in it. Okay, these complex numbers also happen to be functions of t. It's okay. Now, if you let k1 be the number I, then k1 times y1 would be I times I e to the it, and then you would get I. So you get I squared, distributing this through to get I squared e to the it, I squared. I squared is negative 1, so you get negative e to the it, and then you get negative 1. Okay. Now, so what we have here is a vector with complex entries in it. We can call this, let's call this new vector, we'll call this capital Y. Okay, so capital Y is minus e to the it minus 1. Okay. So we've talked about the real and imaginary parts of a number, but what about the real part of y, or the imaginary part of this vector y? Okay, what would these be? Okay, what we'd like to do is to go through that process now. The way you address that is to use Euler's formula. E to the it is cosine of t plus I sine of t, negative 1. Okay. Split out the parts that have complex numbers in them, right? And real and imaginary numbers. Okay, so take a look here. We'll distribute and get minus cosine of t minus I sine of t. And negative 1 is the same thing as negative 1 plus 0 times I. Okay. So what we can see here is that the parts, okay, the ones that don't have, the parts of the vector that don't have imaginary numbers on them, okay, you will split those out, and then you will put I, factor out the I, both of these have I in them, you will get minus sine of t with a 0. Okay, you should double check going backwards here. You check that out. Okay, but if you add these entries and add vectors entry by entry, you will get back to the previous step. So what we can say here is that this vector y had a complex number in it, but it splits into two vectors. The real part of the vector y is minus cosine of t negative 1, and the imaginary part of the vector is this vector minus sine of t, 0. And as in our other example, even though it's called the imaginary part, there are no i's here. You factored out the imaginary number, and the imaginary part of the vector y is a vector that has no imaginary numbers in it. So what we've shown here is that a vector y, right, of t, can be split into two parts. Its real part added to its imaginary part. So times I. So the imaginary part of the vector and the real part of the vector are themselves vectors that don't have any imaginary numbers, and the I is because you factored it out right here. Okay? So that's the complex arithmetic that we'll find that we're going to need, and these are the kind of ideas that you're going to need in section 3.4.